In section 9.6, we're going to talk about something. You see, if you haven't noticed this, we've had a lot of conditions that say, well, for integral test, you have to have positive continuously decreasing. For the comparison test, we had to have positive terms, and we had to compare it. For limit comparison test, we had to have positive terms. How do we deal with negative terms? Well, one way we deal with negative terms is alternating series test. That's when it alternates. We go positive, negative, positive, negative, positive, negative. That's great, no problem. What if it doesn't alternate? How do we deal with negative terms if your sequence from which your series is built does not alternate? And that's what this comes in. It says, well, you know what you can do? You can do what's called absolute convergence. I'm going to show you what absolute convergence is. I'm going to tell you when you should be using it. I'm going to give you two tests that are built upon the absolute convergence idea. These are some of the most powerful tests that you have. Okay? One very, very powerful test called the ratio test, which we're not going to get to today. We'll get to next time on this video. So here's what absolute convergence says. If you're given a series, if you take the series and you take the absolute value of the terms, so you take the absolute value of the sequence from which your series is built, what that would be, for instance, would be a sub 1 in absolute value, plus a sub 2 in absolute value, plus blah, 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 forever and ever and ever and ever. So basically, it changes any possible negative terms into positive terms. Do you guys get the idea of what absolute value does? Yeah. So absolute convergence says, hey, you know what? Consider you got a series, no big deal. Take an absolute value of that series, and it's just going to be an absolute value of your terms, all of them added together. Is there ever going to be something you subtract? Is there ever going to be a negative?
No.
Okay. If this thing is convergent, so if this is convergent, then we say the series that you got this from is absolutely convergent. So we okay. Is a series convergent? I don't know. I don't know if it's convergent. Let's do the absolute value. If we do the absolute value and the series of the absolute value of a sub n converges, then this original series is called absolutely convergent. I'm going to try to go quickly so I get you at least one example. But let me show you what this is for. So this is used for things like this. It's used for lots of things, but especially things like this, which we're going to deal with this example next time. Series of sine of 2n over n squared. Tell me something. Is it always positive?
No.
No. Is it always decreasing? No. Tell me something. Is it alternating? No. Because sine is continuous and goes like this between -1 and 1 the whole time. So is it alternating? No. There's a series of terms where it's like negative, 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 positive, 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 positive. So is it always positive? No. Is it alternating? No. It's not always positive, and it's not alternating. This is where we'd use absolute convergence, for sure. It'd be very easy with this, and I'm going to show you that probably next time. So not alternating, not always positive. Let me give you an example that we can do. We can do this one next time, but I'll show you in a minute. How about that one? Series from 1 to infinity of -1 to the n minus 1 over n squared. Tell me something you know about this series. You should know it because it's alternating. That's right. Is the limit equal to 0 of that sequence from which your series is built? Yes. And is it always decreasing?
Yes.
Yes, it sure is. We know that's convergent. Check out what absolute convergence says. It says, hey, how about this one? How about if I just go, well, let's do the series of the absolute value. What would an absolute value do to this right here?
Make it positive.
So this would be the series of 1 over n squared. Tell me something, by the way, are you okay on doing that one? Absolute value of n squared is n squared, no problem. Absolute value of -1 to, I don't care what it's to, it's going to be positive 1. Tell me something about this.
P series and it
Is it a convergent P series?
Yes.
So this is a P series.
P equals 2.
P does equal 2. That says this converges. Now don't stop there. Say one more thing. Here's what this whole thing means, okay? Check it out.
Therefore.
If you take the absolute value of your series, bam, your sequence basically from which you get your series. If you take the absolute value of your sequence in your series, if this series converges, then your original series absolutely converges. Absolutely as being, I took the absolute value, it's absolutely convergent. This thing is so, we say it this way, so series -1 to the n minus 1 over n squared absolutely converges. Now if you're wondering, wait a second, why is that word absolutely important? Why does it matter? I'm going to show you with the next and final example that we're going to do why there's a difference between converges and absolutely converges. You with me? So here's what we're doing. We're taking the absolute value of our sequence and we're seeing whether that new series converges. If it does, then we say our original series is absolutely convergent. You know what, I'm not going to have enough time for this one. I'm going to write it down, we'll do it next time. But here it is. I'll consider this, I'll talk briefly about it right now, but we'll talk more about it next time. Do you recognize that as the alternating harmonic series?
Yes.
Alternating harmonic series is convergent. We proved it with alternating series test last time. How about if I take the absolute value, I get 1 over n. What's that?
Divergent.
That's harmonic series and it's divergent. You can have series that are absolutely, convergent, but not absolutely convergent, which says absolute convergence is stronger than convergence, and we're going to talk about that next time.
So what's the other?
All right, so let's continue our talk about absolute convergence. Now, I left you with this example, and we talked just a little bit about it. So let's consider the series from 1 to infinity of -1 to the n minus 1 over n. There's something we know already from the last section that's alternating series. We know that this right here is called the alternating harmonic series. You guys remember talking about that?
Yeah.
It's alternating. That's the harmonic series. So this was the alternating harmonic series. Also, let's think about alternating harmonic series. Firstly, it's alternating, right? Does the limit of a sub n go to 0 as n approaches infinity? Yes. Is the limit, is a sub n decreasing? By the alternating series test, this is for sure convergent. So it converges. Quick head nod if you're okay with that so far. That's old stuff. All right, now, here's what we know. We know from this section, this absolute convergence, that if we take the absolute value of our sequence from which our series is built, if we take the absolute value inside of our series, and that series still converges, then our original series was called absolutely convergent, because it converges with its absolute value. Does that make sense to you? So let's go ahead and do it. So if we take the absolute value of -1 to the n minus 1 over n, what does the absolute value do for us? What's it going to do here?
You could always remove it.
Yeah, that's right. So what's it do to this series? What's it change it into?
4 over n.
Anytime you have a -1 to any power, you're going to get 1 or -1, no problem. In absolute value, we take the 1 and make it 1. take the negative one and make it 1. It's going to get rid of any of those negatives. So this thing, that's completely gone. What do I get? And the n, does it change the n? No. Now, think back a little further. Tell me what series this is. That's right. Tell me something about the harmonic series. Yeah, you could have also said it's a p series, couldn't you? With a p equals 1. Either way, what do you know about it? That diverges. So this is the harmonic series. And it diverges. Now, let's put this together. So, here's the deal. If you have a series and you take the absolute value of it, and the series that you get after that diverges, what that says is that your original series is not absolutely convergent. Now, here's the problem that students run into here. They go, oh, well, look at this. If I take the absolute value of something and it works out to be divergent, my original series is divergent. Is that true? No. We started out with this claim, right? That's the alternating harmonic series. We already proved it converges. Does that make sense? So when I say, okay, cool, well, let's do the absolute convergence test. Well, if I do absolute convergence and I get something that diverges, all that says, so my original series is not absolutely convergent, or does not absolutely converge. I'm going to say it this way, is not absolutely convergent. Okay, what's that mean? Well, here's the deal. You can have a series that is not absolutely convergent, but is convergent. You know, what? What in the world are you talking about? Well, let's look at it. We have a series here that we know for sure is convergent by the alternating series test. We've already shown it in the last section. We had it. When we do absolute convergence of that same series, we get a series that is divergent. Are you with me still? Saying that my original series, while it's convergent, it is not absolutely convergent because it does not pass the absolute convergence test. It doesn't work. Show of hands if you understand that concept. What this is called the scenario. When you have a series that is not absolutely convergent, but it is convergent. So convergent, but not absolutely convergent. That's called conditionally convergent. Does that make sense to you? So that's the name of it. So when you have a series that converges, but does not absolutely converge. It's called conditionally convergent. So this scenario, so this idea is called conditional convergence. So we got a few things going on. We can have a series that's just straight up divergent. If I just gave you this one, just the series, on the board alone, nothing else around it. Just the series of 1 over n, that's a harmonic series, that's divergent. Nothing to it. Does that make sense to you? Okay, we can have a series that is convergent, but not absolutely convergent. So here we go, alternating harmonic series. It's convergent, it's not absolutely convergent. Or we can have a series that is absolutely convergent. Now here's the thing. Absolute convergence is stronger than convergence. You can see it right here. You can have a series that converges, but is not absolutely convergent. What that means is that anytime you know that a series is absolutely convergent, you know for sure it is convergent. Absolute convergence is the strongest thing that we have. So we have 3 levels. We have divergent, no. We got conditionally convergent. That's kind of like, okay, cool, it's not to the absolute convergence level, but it's still convergent. And then we have like the super one, absolute convergence. So if we can show absolute convergence, that's as good as we can get. Okay, that shows that it's convergent all the time. Absolute convergence is the strongest that we have. If something converges absolutely, it converges all the time. Show of hands if you understand that one. Okay, so we'll make a couple little notes. Absolute convergence convergence, come on Leonard, is stronger than convergence. Other note. If a series is absolutely convergent, you know for sure it is convergent. Let me give you a real quick example right now just to illustrate this. I think I gave you this example in the opening of this section, but we never really worked on it. So here we go. Let's talk about this series. Sine of 2n over n squared. Okay, let's look at it. Let's go through the whole process, all right? Whole process would be, what is the whole process? What would you do first? I would always do the divergence test first for sure. Now, sine of 2n over n squared plus 1, the limit as n approaches infinity. What do you think?
0.
It is 0. Yeah, this is always going between what two numbers?
0 and 1.
And that number's getting really, I don't care what it is, you divide something between -1 and 1 by infinity, you're going to get 0. Does that make sense? Pass the divergence test. Is this a p-series? Not even freaking close. Come on, guys. No. How about a geometric series? There's a sign in it. How about telescoping series? We haven't talked about that one in a while. No. How about integral test? No, I don't want to do that. That'd be really hard to do the integral of. I don't even know if we can do the integral of that one. Okay. No, it's not alternated because sine doesn't alternate just -1, 1, -1, 1. It oscillates between them, that's true, but it doesn't alternate like that. So we couldn't use an alternating series. So the only thing we're left with is, well, maybe we try absolute convergence here. Let's see if that does the trick. We can't use the comparison test because our terms are not always positive. Does that make sense? So we can't use it straight up right now. But what we can do is say, all right, if we do the absolute value, let's consider what the absolute value of sine 2n does. So I'm going to take a little break here for a second. Do you agree that sine of x is always between -1 and 1? Okay, well, by definition, what that means is that the absolute value of sine x would always have to be less than or equal to 1. That's what an absolute value even means by definition. Okay, well, in fact, it doesn't have to be sine x, it can be sine anything. I don't care what you put in there, as long as it's sine of something. The absolute value of sine of whatever is going to be less than or equal to 1. Show of hands if you feel okay with that one. Well, we're going to change this then. We go, okay, well, cool. Well, then what this thing does is this leads us to this statement. Well, if the sine 2n in terms of absolute value is less than 1, if I divide both sides by n squared, which I can do because n's positive, so n squared is positive, obviously, then we have this statement. What we know right now is that the series we know that the series of this sequence is always less than or equal to 1 over n squared. What do we know about the series from from n equals 1 to infinity of 1 over n squared. Tell me something about that. Why are we doing that? It's a p series. Okay, tell me something about the p series. Converges when what happens? Is p greater than 1 here? So we say something about that. We go, okay, this is a p series. We say the p is 2 that's greater than 1, therefore this thing converges. Then we keep on going. Now, okay, we're doing a lot of things. Can you see that we're doing more than one test here? We can do several tests within one problem. We're doing 2 tests right now. We're doing absolute convergence. Well, actually, we did divergence test first. We're doing absolute convergence. Okay, cool. Well, if we do absolute convergence, then we can make this claim. Sine's always between -1 and 1. Therefore, absolute value of sine is always less than or equal to 1. Therefore, absolute value of sine 2n is less than or equal to 1. Okay, well, if that's true, then absolute value of sine 2n over n squared is less than or equal to 1 over n squared. Since I know the series of 1 over n squared is a p series, since I know the p is 2, this series, the series of this sequence here, is going to converge. Tell me something about this series then. By what? Okay, so by the comparison test. This series also converges. We're almost done. We're not quite done, but we're almost done. I want to see if you guys are okay getting down this far. So we start with a series that we really don't have an alternating series test for. We don't have much to do here. We don't have comparison tests or limit comparison tests because that's not always positive. We can't do it. So we go, all right, well, let's take an absolute value of it. We do an absolute value of this thing. We start drawing some comparisons. We compare this to 1 over n squared. Well, what that means is that because the series converges, and our series with the absolute value of it is always less than that, this series must also converge. Now, go back to our original. We're not back to our original yet. So go back to our original. What's it say about this series? We don't stop here. All you've said here is that this series converges. That's true, but is that your given series? Go back to your given series. What's it say about this series then? It converges. Use the correct terminology. It can say what now?
Converges absolutely.
Not conditionally. Converges.
Absolutely.
Absolutely. It's absolutely convergent. Why is it absolutely convergent? Well, when you took an absolute value of it, the series converges. Therefore, this is absolutely convergent. Does that make sense to you? Therefore, our series that was given to us, this sine of 2n over n squared, you always want to make some statement about your original series, okay? You don't want to just go down here and say, convergence. That doesn't tell me anything. What are you talking about? This one? This one? What are you talking about here? We're doing several things. You got to work it back to make some statement about your original series. We're always trying to say whether this thing diverges or converges absolutely or is conditionally convergent. That's the idea here. So therefore, here it is one more time, okay? Did we know anything about this one by itself? No. We had to take an absolute value. Okay, take an absolute value. Well, within the absolute value, we're going to be using a comparison test. The comparison test said, because it's a p series, p less than p greater than 1, and our series here with the absolute values around it is always less than this one. Well, because this converges, then this converges by the comparison test. No problem. Now, this is not this series. This is this series with absolute values around it. Therefore, because this series converges, we say that this series is absolutely convergent. Show of hands if that makes sense to you. Now, absolute convergence is about the strongest thing we can do right now, okay? So if we say it's absolutely convergent, that's the strongest. We say that it's definitely convergent. So we'll say absolute convergent and then be done. Therefore, this series is absolutely convergent. If I say it's absolutely convergent because I had to take absolute value to show convergence here, that's the strongest thing we do at this point. Show of hands feel okay with that one for real. Okay, good. Now, there we go. By the way, if a series has all positive terms, then absolute convergence doesn't really help us all that much. It's just another test for convergence because you have to use something else within that. What absolute convergence says is this. If there's no known test that you have right now and it's not alternating, try doing the absolute value because that's the strongest thing you can do anyway, but then that's going to show you possibly you could be absolutely convergent, all right? Now we have two tests that incorporate this absolute convergence. This is the first one. I told you about it at the opening. The first one's called the ratio test. It's one of my favorite tests. It's a very powerful test. We're going to look at that right now. Are there any questions before we get going on that? Okay. Oh, sorry, ratio test first. So, ratio test. Here's what the ratio test says. It says if you make a ratio between your next term and the given term, so basically on your sequence you'd have a sub n plus 1 and a sub n. If you make a ratio between them, so if if the limit of the ratio between your terms is less than 1, or the limit between your terms is greater than 1, or the limit between your terms equals 1 after you take an absolute value of it. We get 3 different outcomes for our series, and this is what's really nice. It gives you an instant picture of whether you are convergent or divergent, or, well, whether you have to do more work on this thing. So here's how it works. It says, what I want you to do is I want you to compare the sequence from where you're getting your series, right? Here's your sequence. Here's the a sub n term. Here's the a sub n plus 1 term. It's very easy to find this. I'll show you exactly how to do it. Take that comparison. Take that ratio. Please make sure you have it written correctly. Do not invert these two terms, otherwise these are obviously going to be all wrong, okay? So make sure you have your next term over your current term, your a sub n plus 1 term over your a sub n term in every single case. If your ratio, after you have done the ratio and done the absolute value and taken the limit, if that limit exists, and if it's less than 1, if that's true, now it's not going to be negative. Explain to me why it's not going to be negative.
Absolutely.
You're absolutely right. So if this is, if it's less than 1, what we immediately know is that our series, no, I'm not going to do that. Our series is absolutely convergent. If we have this limit of the absolute value of the ratio between these two terms, and it's greater than 1, we know that our series is divergent. If we have the limit of the absolute value of these two terms as a ratio, and it equals 1, it's inconclusive. And then you'd have to try, hopefully, some other technique that you haven't done already. So this is the idea. It's not hard to do. It's really nice. Did you guys get the idea before we could go any further? It's really straightforward, honestly. You do the a sub n plus 1 term over the a sub n term, put absolute values around it. That's what's given us the absolute part of this. Absolute convergence or straight up divergent, no problem. Or it's inconclusive, which we'd have to do something else with. Let me give you an example just to illustrate this right now. Last chance for any questions on this one. Okay. So here we go. You know, many of you might have noticed something right away with this right here, especially this one. Do you always need to do the divergence test if you're going to do the ratio test? You can if you want to, but sometimes it gets pretty difficult to do, especially with like factorials and powers of n and all sorts of stuff. So what's nice about the ratio test is that if you can't do the divergence test right away, you remember the divergence test, right? You do the limit, if it equals 0, you keep going. If you can't do that, or if it's going to be really hard, and you're doing the ratio test anyway, skip it. Just say, I'm doing the ratio test. It's going to show up as divergent if I do that. Does that make sense to you? That's kind of nice here. So it's a really powerful test, shows absolute convergence or divergence. This is the one that sucks though. You do all the work, you get 1, you go, oh man, I got to do something else anyway. So that would be the issue. Let's start off with this one. Tell me something about that. Let's go through all of them, okay? What's the first thing that you would do here? You would do it. You would, because even with the alternating series test, that's part of it, right? So if I do this one, is the limit of this sequence here, is that equal to 0? Try some L'Hopital's in your head. This one's going to go down a power, then down a power, and then constant, right? This one's not. This is going to be 2 to the n, and then, well, ln 2 to the n, and then ln 2 squared 2 to the n. So this one's not going to decrease like that, therefore this limit would equal 0. Does that make sense to you? Also, well, it's not a p-series, it's not a harmonic series, it's not geometric. It is alternating. Do you see it? We already showed that the limit of that thing goes to 0. Is it decreasing? Oh yeah. So right now, if you wanted to, you could use the alternating series test and show this is convergent. Show of hands if you understood that. You could show that right now if you wanted to. Now, I want to show you the ratio test just to illustrate it on something that's a little simple. So here's what we're going to do. Okay, let's try to use the ratio test here. What the ratio test does is it sets you up with a limit and puts absolute value around everything. That's where we're going to get our absolute convergence here. By the way, do you understand that we might try to show absolute convergence with the ratio test rather than just convergence with the alternating series test? What's stronger?
Absolute.
So if we show absolute convergence, it for sure converges anyway. We show it inherently. With the alternating series test, does the alternating series test show absolute convergence? The first example today that we did said no. It can show convergence, but it can't show absolute convergence because some things aren't absolute convergent or convergent in alternating series. So here we go. We're going to try to show absolute convergence with the ratio test. The ratio test works this way. It says what I want you to do is take this sequence from which we're getting our series and put an n plus 1 everywhere. If we put an n plus 1 everywhere, we get -1 to the n. Do you see where I'm getting n from? N plus 1 minus 1 is going to be n. We're going to get n plus 1 squared plus 1 over 2 to the n plus 1. Okay, I really do need a show of hands if you feel okay with that so far. That's about half of us. Are there any questions? Do you see where this is coming from? One more time? Okay. What we're trying to do is we're trying to get this right now. This a sub n plus 1 term. The a sub n plus 1 term means, hey, go to your a sub n, plug in n plus 1. So instead of n, I'm going to have n plus 1. Instead of n, I'm going to have n plus 1. Instead of n, I'm going to have n plus 1. Now n plus 1 minus 1 is n. Question?
Couldn't you just drop the -1 n since it's absolute value?
We're going to talk about that next. Yeah, it's a great idea. And you can after you show me the absolute value. Okay, so right now, no. You got to have it somewhere. But now, here's what you could do, all right? If you wanted to, right off the bat, we just talked about absolute convergence, right? And this is going to show us, with the ratio test, absolute convergence. Do you guys get me? So right off the bat, you could just go, well, let's do this. Let's do absolute value. Let's get rid of that, and then do a ratio test. It's going to work out exactly the same, because all the absolute value does for you is get rid of the negatives. It doesn't do anything else. Show of hands if that made sense. So either way you want to do it, I don't care. The ratio test practically puts the absolute value in there anyway, so it kind of does it all in one fell swoop. Alrighty? That's a good question. Thanks for that one. Now, over. It says, put that over the original sequence anyway. Well, that's this thing. So all you got to do is rewrite that. So here's the main point, okay? Do not invert this or reciprocate this fraction. It's a complex fraction. This always goes on your denominator. Don't put it on the numerator. This thing, just rewrite it right here. So -1, n minus 1, n squared plus 1, okay, all over 2 to the n. You know what, as a matter of fact, I kind of wrote my fraction poorly. This really is -1 times the whole thing, so if you want to be precise about it, the way I wrote it, you really should have some parentheses there. That way we're not algebraically incorrect. It's not going to matter for the next thing we're going to do. Here's why it's not going to matter for the next thing that we do. Like Devin said, what's the absolute value going to do to this? Gone. Absolute value -1 or 1 is going to be 1. This thing, gone as well. So that's what's nice about the absolute value. And like I said, you can do it first, right off the bat, and get rid of it. And then do the ratio test. That's fine. So we're going to have a limit. N approaches infinity. I'm going to do a couple things here. First thing I'm going to do is I'm going to get rid of my -1 to the n's. Second thing I'm going to do, I'm going to take my complex fraction, so ignore these, okay? These are going to be gone. I'm going to take my complex fraction, I'm going to multiply it by the reciprocal. Is that okay with you?
Yeah.
So we have n plus 1 squared plus 1 over 2 to the n plus 1 times 2 to the n over n squared plus 1. This, and then the reciprocal. Question, true or false? I can get rid of my absolute value right now, true or false?
No, false.
Okay. Why is it false?
Because you can still have a negative pop up in there somewhere.
Can I still have a negative pop up in there somewhere?
There's gotta be
Where's n start?
one.
Is this ever going to be n? So if you want to put them here, that's fine. But are you ever going to get a negative here? Here.
No.
Here.
No.
Here.
No.
Do you need absolute value? Okay. So at some point, you should be able to drop those absolute values. Are you with me? At some point. Does it make sense to you? I know we're doing a lot here, but I want to make sure that you are with me. Are there any questions on that at all? So do you, show of hands if you feel okay about where this came from. That's a ratio test. Are you okay that -1s, they're gone. Absolute value negative, hey, gone. That's why we're doing this, to get rid of that stuff. No problem. Reciprocate by, multiply by reciprocal, not a big deal. Can we simplify this thing? Yeah, first the next step, you know I'm going to get rid of the absolute value, not an issue, we just talked about that. What simplifies here? The 2 to the n simplified. You need to know this is going to happen an awful lot on your ratio test, an awful lot. You see, when you have this 2 to the n plus 1, you're going to get a lot of plus 1s, aren't you? Well, understand that this is really 2 to the n times 2. That's really what that is. Does that make sense to you? So instead of this one, I don't want that. I'm going to look at this one. The 2 to the n's are gone. Those simplify. What I'm left with is just 2. Does that make sense? Do you understand that 2 to the n plus 1 is 2 to the n times 2? Because when you multiply common bases, you add exponents, and that has a power of 1 right there. This is this. You can simplify to the 2 to the n with the 2 to the n. And then we have just 2 left. Just a little algebra, but I want to make sure you see it. Let's keep going. Well, that means we got a limit as n approaches infinity. I'm going to drop the absolute value because everything's positive anyway. It's not really relevant for us. I'm going to distribute this thing. This will be n squared plus 2n plus 2 over. This will be 2n squared plus 2. I want you to verify the algebra on your own. Make sure that I'm right on this thing. Am I right? You sure you're okay with that one? So this, hey, that's 2, no problem. This is a great simplification for us. We distribute that, you get 2n squared plus 2. This one, distribute, no problem. Combine some like terms there, and we got that. Now, tell me something about, oh my gosh, this is an easy limit. This is a good one. What's this limit?
Well,
Perfect. Why is it 1/2? I don't care how you do it. You can do L'Hopital's rule, you can do whatever you want with this. That's going to be 1/2. You can divide by large power denominator. Understand that limits are always about leading terms, you get 1/2, whatever you want to do. That's not what I'm trying to teach you here. What I'm trying to teach you is, what's that result say? Go back to your ratio test. If the limit of the absolute value of the ratio is less than 1 or greater than 1 or equal to 1, we have 3 different results. The worst one is inconclusive. Right? These ones, we really don't care what we have as long as we have one answer, right? It fits one of these models. What does that tell you about our original series?
It's absolutely convergent.
It's absolutely convergent, that's right. If that limit is less than 1, we know our series is absolutely convergent. So what we're going to say is, so by the ratio test, are you getting the picture that whenever I say something, I'm saying by this, by that, blah, 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 we're stating what we used. We're saying by the comparison test, because this is a p-series, it's absolutely convergent. Because we did the ratio test here, and it showed this, and this was less than 1. By the ratio test, the series from 1 to infinity of whatever I gave you to start with, is absolutely convergent. And that's really nice. That's really nice. It's a nice, I don't want to say easy test, there's a lot to it, right? But it's definitely not that hard if you know how to use it. Would you like to see at least, let's do like 2 more examples. You guys good with that?
Yeah.
Let's do some examples then. Any questions? Is it straightforward enough for you? Any
So
questions?
this kind of be like our go-to test for most of them.
Oh yeah, I love this test. Now, I'm not going to say go-to because sometimes, I mean, they're so easy that you just, like a telescoping, no. All right, or like a geometric that you can see is geometric, no. P-series, you see is P-series, obviously not, no. Alternating series, yeah, you might do it for that. I'm going to give you some hints at the last part of this lesson. It's not going to be today, but I'm going to go through like when you should use what. I'm going to do a complete recap of all this stuff, and that's going to be kind of nice for you. When you use the ratio test, typically, here's a little preview, when you have factorials, especially factorials, it's like number 1, okay? Factorials, and when you have powers of n. That's usually when you do this.
Is this the only way to prove absolute convergence, or taking the limit of
No, we did it without this
the
before.
absolute? So
we
can that prove it though? Is that a test that you can prove?
Well, absolute convergence simply means when I take the absolute value of a series and it converges, my original series is absolutely convergent. The ratio test incorporates that into it, which is why when I do the absolute value, it's not just convergent. It's absolutely convergent. Okay, so let's look at the series from 1 to infinity of n over n to the n. Just joking. Insert a little humor there. Now let's look at it, all right? Let's look at this. First thing I want you to notice, tell me something about the divergence test. Would you want to do that here? No, I wouldn't either, because n factorial over n to the n, I don't know, man. It's probably 0. I guarantee it is, because this thing's going to, I think it converges. This is going to converge. But would we want to show it? Probably not. Which right there, you go, let me do the ratio test. Why? Why would I want to do the ratio test here? Factorials. And it's so nice with the ratio test, you're going to see why it's nice in just a minute. Let's just look at other things real quick. Is it a p-series? Geometric?
No.
Telescoping?
No.
No. Harmonic?
No.
Is it something that I would want to do an integral test on?
No.
Comparison test? Maybe we could, possibly. Here's why I say that. Are they all positive terms?
Yes.
They are. Which means that absolute convergence, well, it's just going to be another test for convergence for us. What's great, though, the ratio test doesn't care about that. The ratio test just says, hey, I'm going to tell you whether you're absolute convergent or divergent. You don't need to do the divergence test with the ratio test, so it'll be in there somewhere. Does that make sense? So that's kind of cool. Let's do the ratio test and see how this thing plays out. So ratio test said, and you can even write rate by ratio test. So ratio test says do a limit as n approaches infinity, set up an absolute value, even though right now we know it's all going to be positive, okay? We still set up the absolute value because this is what the ratio test does. At least show it on the first step. After that, yeah, they're positive terms, get rid of it, no big deal. but set it up first. So you get in the habit of it. It would suck to, get in the habit of not writing it and then need it here. And oh man, you don't want to do that. Now, let's see if you guys can fill out the numerator of our complex fraction and the denominator. So I'll give you about 10 seconds, see if you can get here and here. Go for it. The denominator should be really easy because the denominator is exactly what this says. That's it. That's our a sub n. The numerator takes a little more work, but not much. This is going to be n plus 1 factorial over n plus 1, use parentheses where appropriate, to the n plus 1. Show of hands if you got exactly that. So everywhere you see an n, you just put n plus 1. That's all it is. Now, let's talk about this for real. Are the absolute values relevant?
No.
Is that positive? Is that positive? Then this whole thing is? So let's drop the absolute value. Also, with the ratio test, you're always going to get a complex fraction. You're typically going to get a complex fraction, usually, with us. So if we get a complex fraction, we're going to create a division problem and multiply by the reciprocal to undo that complex fraction. So we'll have n plus 1 factorial over n plus 1 to the n plus 1 times, what's going to be next? Over? Did I tell you guys are going to get a lot of n plus 1 powers? What typically happens here is you'll have to split off one of those powers, like we did with the 2, like we're going to do with this thing. So don't let this confuse you. We're just going to split one off. Just break it off. Strip it off there. Oops. So we got limit, no problem. We're going to have an n plus 1 factorial. We're going to have an n to the n. We're going to have an n factorial. And then we're going to strip off 1 power of n plus 1. We're going to strip one of those things off. So we're going to put n plus 1 to the n, and we're going to strip one off. We're going to put that little stripper right here. N plus 1. Oh, come on. That was funny. Just joking. Do you understand that this really is n plus 1 to the n plus 1 power?
Yeah.
This is a power 1, right? Common bases. If you multiply common bases, you add exponents. That is this thing. Okay. Well, that's not bad. That'll help us out just a little bit. So, what now? Oh, goodness gracious. Simplify. Can we simplify that? Do you understand what n plus 1 factorial is? Do you know that n plus 1 factorial is the same thing as n plus 1 times, what's the next term? N. Oh, times, this would be n minus 1. Oops. All the way down to 1. Does that make sense to you? Tell me what this is. Ah. Therefore, by your own little logic here, not little, I didn't mean you, by your own logic, this is the same thing as n plus 1 times n factorial. Let's see if you can wrap your brains around that. Does that make sense to you? If this means n times everything previous to it, and I multiply by n plus 1, that gives me n plus 1 factorial. This is n plus 1 times n factorial. N plus 1 times n factorial. That is the idea. Show of hands if you feel okay with that one. Get used to it. You're going to do that a lot. Okay, so let's go here. So what I'm going to do is I'm going to write the limit. And we're going to have n plus 1 times n factorial over this guy. We had n plus 1 to the n times n plus 1. This guy was n to the n. This is n factorial. Do you see any things that can simplify now? By the way, everything we're doing right here is algebra. There's no calculus involved right now. It's all algebra. It's understanding that this is a complex fraction. In fact, even doing this is the only calculus you really do besides taking a limit at the very end. You're going to do something. It's not going to be that easy to do some of the limits, but calculus here, all algebra to simplify. That's really it. Understanding that that's a complex fraction, no problem. Understanding this right here is n plus 1 times n factorial. That's a big deal. Understanding this is n plus 1 to the n times n plus 1. Okay, these two don't change at all. Let's see what we can simplify. Give me something. N factorial is gone. Oh, that's a huge deal. Those are gone. What else? The n plus 1s. That was good, important too. So what we end up with is a limit as n approaches infinity of n to the n over n plus 1 to the n. You see, the idea here that I was trying to get to was two terms which have the same power. Did I get that? Simplify as much as I can. I got that. Well then, if they do have the same power, I can get n over n plus 1 to the n. We're almost home. Almost there. Now this is where it gets a little weird, right? I want you to think of this for a second. I want to open your memory banks here right now, folks. Hopefully you have some cash to withdraw from. Otherwise your memory banks are whatever. Plug in infinity, what do you get? No, you don't. What do you get in here?
Less than 1.
Nope. You get 1. This is 1. This is infinity. You get 1 to the infinity. That's an indeterminate form. Remember indeterminate forms? When you had a 1 to infinity, oh, this is where we went, oh, let's do e to the limit of ln of a bunch of junk. Do you remember that? And then we did a bunch of junk because you move your power forward, you create a fraction, you use L'Hopital's rule. All right? You're going to have to do things like this. Now, I'll give you a couple hints. Most of the time, what we like are fractions that you can split apart. We don't like n over n plus 1. We like n plus 1 over n. So when we do that, maybe do a couple nice little tricks here. Do something like this. Do the n plus 1 over n. Now, does anyone know about this? If you reciprocate a fraction, what happens to that? Negative. This becomes negative. This becomes negative n, which means I can write this as 1 over n plus 1 over n to the n. Now, I'm going to cheat, okay? Well, I'm not cheating, I did it on the side. I'm not going to re-show you this. This limit from n to infinity of n plus 1 over n to the n. This, do I have time? Do you guys want to see it?
Yeah.
It would be like a minute, 2 minutes over, but here it is. Firstly, do you understand it's 1 to the infinity? Okay, that's bad news. What that means is we do e, limit n approaches infinity of a bunch of junk to the n with an ln in front of it. That allows us to move our n forward. For the sake of time, I'm going to not write just that little part. When we have that, this is now an infinity times, sorry, that's ln. Times 1. Okay, so we're going to have to redo that one. So that's e to the limit ln of n plus 1 over n all over 1 over n. Now we can do a L'Hopital's with this thing. So if we do a L'Hopital with this, we're going to have e to the limit 1 over n plus 1 over n times negative 1 over n squared, all over negative 1 over n squared. The derivative of this is this, the derivative of this is this. You're going to have to follow me. Are you guys with me on that one? I know I'm doing it fast. Well, this is kind of nice because those are completely gone. So this is e to the limit of 1 over, if I divide both of these, I get 1 plus 1 over n. Remember that n is approaching infinity. What's 1 over infinity? 1 plus 0? 1 over 1? E to the first. That limit is e. Therefore, this thing right here, so this was just its own little guy. what that says is that the limit, I didn't really want to show that, but now that you have it, I'm sorry, what's the limit of this thing? This is 1 over E. Now, tell me something about 1 over E.
Yes.
That is less than 1. This is less than 1, and so we're going to finish this thing off. What test did we do? Ratio. Let's talk about our original series. Tell me something about the ratio test. Was it conclusive? Did we get anything out of it? When is the ratio test not conclusive? Very good. This thing wasn't equal to 1, therefore we have some conclusion. The fraction, the ratio, was it less than 1 or greater than 1? What's it tell you about our series? You're absolutely right. What I want to know is if that made sense to you. Okay, let me ask you a different question. Did it make sense up to this part? Show of hands if it did. Okay, were you able to follow that one? That's old stuff, all right? So you gotta, this is the section where we did the indeterminate form of limits. You might have to do that within part of it. Understand you can take a piece of this, do the limit, put it back, and then you follow up with that ratio test. You guys okay with that? Well, one more example, then I'll do a recap next time. All right, here we are. So let's do our last example of using the ratio test. Then we'll talk about the root test, and finally a recap of everything that we've done in our series thus far. So, getting started. First things first, what's the first thing that you would probably do here? You could try lots of things here. This is going to alternate for sure. I probably might just jump straight to the ratio test because we have that negative in there, because we know it's nice, and because unless it's inconclusive, it gives us the result that we want, either divergent or convergent. You see, some of those other tests, they don't do that. Some of them are just, well, if it does this, then it's this. This one says, well, we have 3 outcomes. We have absolutely convergent, which means it's definitely convergent. We have it's divergent, which you're done anyway, or it's inconclusive. If you get, listen, on your homework and stuff, they're going to ask you for a couple things, right? They're going to ask you for whether this series is absolutely convergent, conditionally convergent, or divergent. Does that make sense? Mm-hmm. If you want to check for absolute convergence, you have to do an absolute value, which means you're probably going to use the ratio test at some point. So how you go ahead and do those problems, you start with a ratio test or the root test, which we're going to use. You start with that. If it works out to, hey, it's less than 1, you know you're absolutely convergent, you're done. That's stronger than convergence. If it works out to fraction greater than 1, no problem, you're done, it's divergent. No need to go any further. If it works out to 1, then you start using another test after that question.
Now, what if it's infinity? That's over 1.
That would be over 1, yeah.
But
if it's 0.
So it counts as...
Absolutely.
Okay.
Yeah. Okay, so let's start here. Let's try the ratio test on this thing. So first thing with the ratio test is what? What do we do with the ratio test? You look at me blankly. That's a good start. What do we do with the ratio test? How do we start that thing
Find
off?
our a sub n.
Okay, it's a limit. That's very good. So we got a limit. A limit as of what? That's right. In fact, I think I told you this last time. If you wanted to, could you do the absolute value here and then compare the ratio? Yeah, the absolute values are going to take all those negatives away anyway, make all positive terms. So you could do that as well. Most people just do it all in one step, the way that I'm going to do it. By the way, what goes on the main numerator of this complex fraction we're creating? Is it the a sub n or the a sub n plus 1? So we're going to write that. So a sub, I'm a little crooked here, a sub n plus 1. And we're going to be real careful about it. What's our a sub n plus 1? How would that look?
Wherever there's an n,
To the n.
Okay. To the what?
N power.
Very good. And then what?
n plus 1 squared.
And then what?
3 to n plus 1.
Perfect. We'll end those absolute values. On the main denominator, it's just a sub n again. So it's negative 5 to the n minus 1. It's n squared and 3n. Now what would you do? If this was your problem on a test, what would you do here?
Remove the absolute.
How would I remove the absolute value? How would I do that?
If they're all positive anyways.
Sure, so look at, you can do that actually right now if you really want to. If you did the absolute value of negative 5 to the n, you're going to get 5 to the n. What you can't do is just say, well, when I take the absolute value, that just goes away like my negative 1 to the n. That you can't do. Do you guys see the reason why? So the reason why this actually works is negative 5 to the n is the same thing as negative 1 times 5 to the n, which is the same thing as negative 1 to the n times 5 to the n. Which means that, yeah, okay, you can get rid of the negative, but you can't get rid of the 5 to the n. Are you sure you're okay with that? Okay, so we can do that now as well. Also, would I want to leave it as this complex fraction idea? Does that? No. So I'm going to drop the absolute value. That means I'm going to get rid of my negatives. I am not going to get rid of the n or the 5. I'm not going to get rid of the n minus 1 or the 5. I need those things. And I'm also going to, instead of having the complex fraction, we'll have one fraction times the reciprocal of our other fraction. So here we'll have 5 to the n over n plus 1 squared times 3 to the n plus 1 times, what's going to be on our numerator over here?
Square root times 3n.
Perfect. All over?
5.
Quantity of
To the what?
N minus 1.
Perfect. Yeah, that's exactly right. Why would it be negative 5?
your absolute value.
Our absolute value would take care of all that stuff. So no more negatives. What now? Stop.
Simplify.
Simplify. Simplify as much as we can. Tell me some things that simplify. Yeah, okay. So if we have 5 to the n minus 1, we have 5 to the n. How much do we have left, and where does it go?
5 to the -1. It'd be, ooh.
5 to the n.
Do you understand that what 5 to the n really is 5 to the n minus 1 times 5? Do you guys get that?
Mhm.
So if this is 5 to the n minus 1 times 5, then the 5 to the n minus 1 would simplify, and we would have 5 left. Are you sure you're okay with that? It's just algebra, but I want to make sure that you're all right. Yes, no? You guys over here, are you okay with that one? Okay. Moving on. What else? What else simplifies? Come on, quickly. We got to move on to stuff. What else? The 3's. Okay, so we got 3 to the n. We got 3 to the n plus 1. Understand that 3 to the n plus 1 is really 3 to the n times 3. Well, if this is 3 to the n times 3, what can I simplify out of that? 3 to the n's are gone. What's remaining?
3.
Okay. I'm going to move over here just so I can write this a little bit nicer. So we have a limit as n approaches infinity of, well, let's check this out. We've got, well, first we got a 5, and we got a 3. So we got a 5/3, we've got an n squared over n plus 1 squared. Quick show of hands if you're okay with that one so far. Okay, next up. Notice how the n and the n plus 1 both have the same power. Let's make them one fraction to that power. So we'll have a limit, n approaches infinity, of 5/3 times n over n plus 1 squared. Hey, tell me what's going to happen here. What would you get? What happens to our limit as n approaches infinity? We get 1? The whole thing's 1? Let's go part by part, okay? How much is the limit of n over n plus 1? That's 1. Do you understand why that's 1? You can divide everything by n if you wanted. You can do L'Hopital's on the inside of that if you wanted. Either way, that's going to be 1. How much is 1 squared? 1 squared is 1 times 5/3 is... That's a horrible 5/3. Now, tell me something if the limit of the absolute value of the ratio between my n sub n plus, a sub n plus 1 and my a sub n term equals 5/3. Is that a conclusive result for this ratio test? Is it conclusive or inconclusive? It's definitely conclusive. It tells us something. Now you gotta know what it tells us. Inconclusive would be when that equals to 1. Yeah, then you gotta do something else, all right? You don't know anything about that. But this one equals 5/3. Is that bigger than 1 or less than 1?
Bigger.
What's that tell you about our series that we got? I don't care about absolute divergence. There's no such thing. It's just divergent. Okay. I don't want you to say absolutely divergent because that sounds weird. All right. If you say absolutely divergent, you could mean it's not absolutely. Listen carefully. It sounds trivial, but it's not. Okay. If you say it's absolutely divergent, that's kind of weird because, well, does that mean that it's just simply not absolutely convergent, but it might be convergent? That's called conditionally convergent. Or do you mean that it's divergent altogether? There's no absolutely divergent. There's absolutely convergent. There's conditionally convergent, where it does not absolutely converge, but does converge. And then there's divergent. So according, let's say it properly, what's this one do?
Divergent.
According to what test?
Ratio
So we
test.
say, hey, by the ratio test, the series that we had to start with, diverges. And that is the whole thing for the ratio test. Show of hands feel okay with the ratio test. Okay, are there any questions at all before we go on? Is it pretty straightforward to you? Question?
I just want you to go over that, like how that 5 to the n minus 1 times 5 equals 5 to the n. Like, so
How much? What's the power here?
1.
Add the powers.
Oh, because of the absolute, the negative disappears?
Nope. If you
No.
add 1 plus
1
n minus
minus
1, you
1
get n.
Ah, alright.
Okay. Last test. Last one. Aren't you excited? I'm kind of excited. The last one, we've done so many of them. The last one we're going to cover these, is called the root test. Use the root test if you have nth powers in your series. Now, we talked about the ratio test, right? I said you use that ratio test if you have factorials or nth powers in your series. So what that means is there's like a crossover. A lot of times you can, not a lot, I don't know, some of the times you can use both of these tests, either one of them. You can use the ratio test or you can use a root test. It just depends on which one's going to be easier for you. What I would not recommend is using the root test if you have factorials. Use the ratio test for that. So when the root test is typically used is for a series involving nth powers. What's really nice about the root test is that after you've covered the ratio test, the outcomes are very straightforward. So here's what we do. If we take a limit, starts up exactly the same way as the ratio test. We start with a limit. If we take our sequence from which we get our series, and we take an absolute value of it. Do you notice something that's different about this test versus the ratio test already? What's different about it? Is there a fraction at all?
No.
There is no ratio because this is not a ratio test. All right, this is a root test. So instead of creating a ratio, we're going to create a root. So here's how it works. We take the sequence itself. The main advantage here is that you don't have to have a really large, well, I erased the board, but a really large fraction out of this one. There's no such thing. It's just the sequence from where we get our series, the a sub n. Then you take an absolute value of it, and then you take an nth root of it. What's nice is that if this thing exists, I'm going to try to make this a little clearer. If that limit exists, so we start with our sequence, no problem. We take an absolute value of it, no problem. We take an nth root of it, and then we take a limit as n approaches infinity. If this limit exists and is less than 1, it has the same result as if the ratio test were less than 1. What's it going to tell you about our series?
Absolutely convergent.
That's very good. It's absolutely convergent. What about if the limit is greater than 1? What do you think? Yeah. What about if the limit equals 1? What do you think? Same results. You guys okay with the root test? Probably not yet, right? You want to see an example? Let's do an example here real fast, just one of them, to give you an idea about how you can do this. Again, I'll make this statement one more time. Can you use the ratio test for sometimes you could use a root test? Can you use the root test for sometimes you could use the ratio test?
Yes.
Yeah, you can. There's a lot of crossover there, right? Again, what I wouldn't recommend, don't try this if you get factorials. The ratio test is really nice for factorials because when you just add 1 to a factorial, most of that stuff is gone. Make sense? So keep that in mind. But let's try one example just to show you how it works, and then I'll do that recap I've been promising you. So let's start with this series. You know, a lot of times students have questions, how do you know what test to use? What do you start with? Well, you start with, firstly, you know what, I'd start with through all our process and see what's going to be the easiest thing for us to do in each case. I know that's alternating. Do you guys know that's alternating?
Yes.
Is it going to be easy to show that it is decreasing? Or to show that the limit equals 0?
No.
Those aren't going to be easy things to do. So I probably wouldn't do an alternating series. It's not a p-series. It's not a geometric series. It's not a telescoping series. So the first thing we come to is like, well, all right, integral test? No, it's not, I don't know. That's not all positive terms. You can't even do it. Comparison test? No, it's not all positive terms. You can't even do it. So what you could do, you could take the absolute value of the whole thing and then try one of those, couldn't you? You could do that and then try a comparison test, then try an integral test. But those things look pretty hard for this one because we have to show decreasing for both of them, for integral test and comparison test. That wouldn't be a good, for integral test and for alternating series test, we have to show decreasing. Comparison test, well, you'd have to figure out what this is smaller than, then show convergence, or bigger than, then show divergence. Probably the quickest way to go about one of these ones, because it has the absolute value already, is the ratio test or the root test. You with me? And I believe both of them would work, but I'm going to show you why you might want to choose I don't know, I haven't tried the ratio test on that one. Maybe you can try it on your own and see if it actually does work. Maybe I'll do that later too. I would try the root test, and here's why I try the root test. What I'm seeing is that I have this to a power n, I have this to kind of a power n, I can make it a power n. So if I take an nth root, those things are going to go away. The absolute value is going to make this thing go away. Does that make sense? So let me show you how the root test works. Root test says, hey, take yourself a limit. N goes to infinity, and nth root of the absolute value of whatever you have here. You don't need to do an n plus 1, which is kind of nice. You don't have to create a ratio or do anything or change this sequence where we get our series from in any way, shape, or form. And already we can start working with it. So let's go through it one time. Firstly, show of hands if you're okay getting from here to here using the root test. Are you okay with where that's coming from? It's nth root, it's the absolute value, it's the same exact thing you got. Now, let's work on it. Absolute value of -1 to any power. What's going to happen with this thing? It's gone. Completely gone. So we got a limit. N approaches infinity. Yeah, it's still an nth root. But this, the absolute value of -1 to any power is 1. So this piece is gone. Now, 2 to the n plus 3. When you're doing the root test, you're trying to match up your powers. So if I have 2 to the n plus 3, I'm not going to write that as 2 to the n plus 3 again. What I'm going to write is 2 to the third times 2 to the nth. Are you okay on the algebra with that?
Mhm.
That's still 2 to the n plus 3. That's exactly what that is. By the way, if you would have had like 2 to the n minus 3, 2 to the n minus 3, you can change this to 2 to the n. Oh, that's not even an n. Come on, Leonard. Get rid of it. Times 2 to the negative 3. Couldn't you do that?
Yes.
That would just go to the denominator and be 2 to the third. So don't get stuck on this and go, oh my gosh, I can't do it. Well, yeah, you can. Just separate off that negative exponent, move it to a denominator, and then it's that simple. Does that make sense to you? So don't get all hung up on that. All over n plus 1 to the n. Now, let's try to make this all have one power if we can. So here we get 2 to the n, we get n plus 1 to the n, we get 2 to the third. 2 to the third I'm not worried about. Here's why I'm not worried about that. I can separate products when they're inside of any sort of a root. So I can separate this as 2 to the third times 2 over n plus 1 to the n. Furthermore, because I've separated this, I can make this a limit as n approaches infinity of the nth root of 2 to the third times the nth root of all this junk. 2 over n plus 1 to the nth power. Now here's what I'm going to ask you. Do you see why I tried to get these two things to have the same power? Do you see why? The idea is if I can make them have the same power, I can do this with it. What's the nth root out of something raised to the nth power? What's going to happen there?
So n's count.
They're gone. So we get a limit as n approaches infinity of, by the way, do you know this? I know you know it. When you have a root out of something raised to a certain power, we get the base to the power over the root. Did you know that?
Yes.
Okay. Times 2 over n plus 1. Let's consider that. Let's see about n going to infinity. So you tell me, what's 3 over n when n goes to infinity? Can we do that?
0.
What's 2 to the 0?
1.
Okay. So this is 1 times... what's 2... Oh, how about that one? What's n as n approaches infinity?
Oh.
This whole... Okay, the whole thing. You guys are better than that, aren't you? 2 over this. What is that?
0.
0. What's 1 times 0?
0.
Okay. Is that conclusive or inconclusive? When is the only time a ratio or root test is inconclusive? Is this equal to 1? Then there's a conclusion here. Is this greater than 1 or less than 1?
Less.
Hopefully, yeah. So what does that tell you about this series? Is this series absolutely convergent, inconclusive, or divergent? What is it? Very good. So we say it by the root test. We tell me what we're doing. Our original series here is, one more time, if the result you get is less than 1, what do we say about our series?
Absolutely convergent.
That's exactly right. Quick show of hands, you feel okay with that so far? Are you all right with that one? So we go, all right, well, what would work best here? Well, probably not anything we've done before. What's quickest, what's nicest is a ratio test or a root test. It'll give us a nice conclusive answer most of the time. If it's 1, then you try something else. In this case, you go, well, what's going to be better for us? A ratio test or a root test? Root test probably because I have an nth and an nth I can make those have the same power. I know that the root is eventually going to get rid of that, and we'll have no problems with this. Results are the same for the root test as they are for the ratio test. You sure you're okay with it? Now, we've come a long way, haven't we? We've done a lot of stuff on this idea of series. What I'd like to do now is give you a summary of everything we've done and when to use it. That way, when you get to your test or your homework or whatever you're doing, you go, man, what am I supposed to do here? Maybe you can break this down like a little outline or have this in your head, what you should look for to make the problems as easy as possible. Any questions or comments or anything before we get going on that? Would you like that little summary?
Yes, please. One more kiss, please.
Well, typically a book will have something like this in it. I think ours does too. But I would like to give you kind of my version of it as well, things that you should be looking for. So, here's a summary. The number one thing we look for in any series, number one thing we always test for in any series is, if we can, if it's nice and easy, we do the divergence test. We kind of skipped over that one on this one, because what's nice about the ratio and the root test is it almost inherently does that, because when you get down to here, if you have something greater than 1, you know it diverges anyway. So it kind of does that for you, which is nice. But most of the time, almost all the time, we're going to do that divergence test first. So, number one thing we check for is if the limit of a sub n does not equal 0. The series of a sub n diverges. This is what we call the divergence test. Take a limit of that sequence from which we get our series, and if that limit of that a sub n does not equal 0, you're done. It diverges. Number 2, we can also do series, what I call, what's the matter?
Push infinity.
Say what now?
Limitations of push infinity.
What did I do? Oh, shoot. You know what? I thought about that 0. I'm sorry. Mine was ahead of my hands. So, yeah, you're right. If n approaches to infinity, that's right. And a sub n, the limit of a sub n does not equal 0, our series diverges. Next one, we got several types of series we dealt with. So we can do this by type. For instance, if you know it's geometric, I'll just leave it that way. So if we know it's geometric of that form, remember this could be to the nth power as well. When does this converge?
When absolute value R is greater than 1?
Between -1 and 1, so the absolute value of R would be... So if we know it's geometric, stop. Don't do any ratio tests or root tests or anything harder than that. If it's geometric, man, make it geometric. Manipulate it to fit this thing, and then we know it converges if your R, absolute value of R is less than 1. Also, what's nice about geometric is there's a sum built into it. The sum is A over 1 minus R. It's a sum for us. What else do we got? Oh yeah, when does it diverge? Thanks a lot for the help on that one, guys. More than or at least 1. By the way, if you check for, should you do the sum first on a geometric, or should you check for convergence or divergence first?
Convergence is divergence.
If the geometric series diverges, would you want to do this on a test? I will mark you down for that. You say, the sum is this. No, it's not. It diverges. So you can't tell what the sum is, okay? Don't do that. Okay, next one. We had telescoping series. For telescoping series, the basic idea here is use partial fractions to get some, so remember the partial fractions we did? Use partial fractions to get a partial sum. So we start with partial fractions. To get S sub n. That's our partial sum. And then we take a limit of S sub n as n approaches infinity. We go, okay, here's what we have now. Now let's say this n goes to infinity. So we say, here's our sum up to a certain point, move that point to infinity, and we get whether this telescoping series converges or diverges, and we get a sum for it. course, I'm not reteaching you all this. We've already covered all this stuff. I'm just kind of recapping, okay? Okay, last one by type. Last one by type. The last type of series that we had was what?
Alternating?
Oh no, I'm sorry. Kind of different. The type, like a named type. Like we had geometric, we had telescope, and we had P series. That's right. So P series. If we have 1 over n to the P, that's a P series. Do you remember when a P series converges and when the P series diverges? Yeah, it's easy to get these confused for some people to go, oh man, geometric, great, lesson 1, oh, what happens? It's different for this one. So a P series converges if, I'm sorry, when do you say it converges? If P is what?
Greater than 1.
And when does it diverge?
Less than or equal to 1.
That's what I was looking for. Where's the equal to go?
Harmonic.
Okay, so what's that going to be, the equal to? Is it going to converge or diverge?
Diverge.
Yeah, that's right. That would be diverges. You're exactly right. If I have the equal to one, that gives me the harmonic series. We've already talked about how that diverges. Anything else greater than 1, well, it's going to converge. Less than 1, it's going to diverge. Also, we talked about this a while ago, I'm not going to write it down, but you need to know that a lot of times we can manipulate our series to fit one of these. So all of a sudden, we might not have it immediately, but we work on it a little bit, we end up getting a geometric, or we end up getting a telescoping, we end up getting a P series. And then if it's by type, man, this is really nice, because it's super fast. And for at least 2 of these, we can find the sum for it. The other ones we can't, but for these 2, we can actually get the sum. You okay with that so far? Yes. So. So, if you've done the divergence test and it passes, and if it's not a specific type, so it's not a geometric, and it's not telescoping, and it's not a P series, the next thing you might want to look for, maybe, some people skip over this one because they see, well, I'll probably go to a ratio test. You might try the integral test. Integral test says that if you have a function, I'm going to use some poor notation, but I'm just going to do it anyway. If you have a function that represents your sequence from where we get our series, and the function is positive, continuous, and decreasing, on an interval from 1 to infinity. Actually, you know what? This is a little bit of a, not a mistake, but kind of, we don't need it from 1 to infinity. If you remember this, we can add and subtract a finite number of terms to our series. So even if it's not till like 3 to infinity, we had a couple of those problems, right?
Mm-hmm.
Where it was, okay, I started at 3. That's fine too. It just has to be positive, continuous, and decreasing on some interval forever starting at a certain point. Some big N, not little n. But if we have that, we can model a function after some sequence where we get our series, and the function is positive, continuous, and decreasing on a certain interval, then we can do the integral test. From wherever your interval starts to infinity, of course that will be an improper integral because we have 1 to infinity here. And what this says is that if this thing converges, series converges. If this thing diverges, series diverges. So, function, positive, continuous, decreasing on an interval, not a problem. Do an integral test from 1, wherever your interval starts, to infinity. It's an improper integral. If you find out that it equals a number, cool, it converges. If it doesn't, well, hey, diverges, not a problem. Number 4, if we have a sequence, a series from where all the terms are positive, and the series acts like a p-series or a geometric or something else that we can do, like a generally geometric p-series, or well, harmonic is a p-series. So if it acts like one, we do a comparison test or a limit comparison test. We say, hey, this is smaller, always smaller than something, or it looks like another series, kind of, it has maybe missing one little piece to it. We can do a comparison test or a limit comparison test. So when we did that, we knew that if we could find another sequence really where every term of our given series was less than the known series, if we know that, and the series of b sub n converges, then the series of a sub n also converges. If a sub n is bigger than b sub n, and the series of b sub n diverges, series of a sub n also diverges. And lastly, this of course would be for the comparison test. So the comparison test says, hey, you know what, if you know this, if you know that every single term in your a sub n is less than every single term in your b sub n, and the series of b sub n converges, a sub n converges. If this every term in a sub n is bigger than or equal to every term in b sub n, and b sub n diverges, a sub n is bigger than that, it has to diverge. This is for the comparison test. The last one's a limit comparison test. Says, hey, you know what, if you take a limit of a sub n over b sub n, don't get this confused with the ratio test. This is not the same thing. The limit comparison test does this with two different series here that look a lot alike, okay? So if this thing exists, naturally these would both be positive terms, okay? So your limit would have to be positive as well. If this thing exists, then the series will have same result, both convergent, both divergent. Okay, I'm going to keep moving, but you guys have any questions on this? I'm going to have to erase this as we go. Unfortunately, I'm short on wall space, so are we okay with this? Hello, yes, no?
Yes.
Shouldn't be new stuff, really. It should be old stuff, but I want to make sure that you guys are okay on what I've written down. Which one do we do? Conversion test? So, number 5. Okay, number 5. For a series where we have -1 to the n, or -1 to the n minus 1, times some other sequence that has all positive terms. That's your alternating series. You know what, this one should be pretty fresh. You guys should tell me. This is a two-part test. Part A, what's part A? Limit of what? And everybody, what's it got to be equal to?
Zero.
Yeah, that's practically the divergence test again, just part of it. So limit, got to be 0. Also, part B, what else has to happen?
Yes.
Got to be decreasing, that's right. So the derivative of a function that's modeled after your sequence has to be negative. Negative means decreasing. Or if you show this, the next term is less than or equal to the previous term. In other words, if it's decreasing, then the series converges. So far so good on these ones? The last two we just did, so I'm not going to be kind of super explicit on the last two. What I'm going to tell you is that on number 6, if you want to do ratio test, here's when you should try the ratio test. Try the ratio test for factorials and nth powers. By the way, you guys know what the ratio test is, right? I don't want to kind of recap that. We just did it. Is it a sub n over a sub n plus 1 or a sub n plus 1 over a sub n? And then we take an absolute value. This will show you absolute convergence, divergence, or inconclusive. When is this going to be absolutely convergent?
What is less than 1?
When the limit of the ratio is less than 1. That's right. So, and if it's greater than 1,
Divergence.
and if it's equal to 1. You have that in your notes somewhere, right? It should be previously on the video, actually. Number 7. Try the root test for nth powers. As I said before, sometimes you can do either one of these tests and get the same result out of it. Now, what I'd like to do for the rest of our time here, I'm going to briefly, I mean like so fast, go through some of these problems just to give you an idea about how I would look at them and say, oh, you know what, I'd try this here, I would try this here. We're not going to do hardly any of them, okay? We're just going to look at it. Does that make sense to you?
Yep.
So let me write them all down, and then we'll go through them very fast. Okay, there we go. I want to give the rundown here because I think it's really important that you guys see this at least one more time. Do you have them all written down?
Yes.
Okay, so let's go through it. First thing we check for every time is always the divergence test. So on number 1, problem number 1, what's the first thing you're noticing up here?
It's 2/3.
The limit's going to equal 2/3. Not equal 0, diverges. It's that fast. Don't worry about looking at telescoping or anything else. It's going to diverge. Does that make sense to you? Next one. You know you can separate series by addition or subtraction. Then in this case, you'd have something that is, well, that's a geometric. This is geometric with 2 1/3 to the n. Do you see it?
Yes.
This, you need partial fractions, that's going to be telescoping. So you get geometric and you have telescoping. Both of them would have to converge in order for this series to converge. You with me? Okay, so this is geometric and telescoping. Next one. Well, we go, okay, geometric, no, telescoping, no, but this can look like a T-series. Make them into a type of series if you can. Divergence test, cool. Geometric, no problem, we can make it geometric. Telescoping, partial fractions for telescoping. Here we have okay, this is a P-series, where P is greater than 1. That thing is going to converge, it can be that fast. Next one. For something like this, well, it's really easy to see that this is always positive. It's always continuous for n greater than 3, as it says right here. It's always decreasing. We don't even have a numerator besides 1. And the integral would be really easy, because if you use a substitution of u equals ln of n gives you 1/n. It's right there. This is going to be u to the negative 1/2, and then we do an integral of that. So integral test for this one. Next up, that one. Well, here's the difference between these two, what you should do and when you should do them. A lot of times when you have single, you see what I'm saying about single terms? There's not multiple terms here. When you have single terms, do a comparison test. This will be less than square root of n over n squared. Do a comparison test with that. This would be n to the 3/2. This is a P-series. P is greater than 1. It's going to converge. Therefore, because it's always less than that by the comparison test, this series also converges. Does that make sense to you? So comparison test. Here, when you have more than one term, it's really hard to do this because you don't know what's less than. You don't know what's greater than because you have these other terms being added on or subtracted. That's really hard. Does that make sense?
Mm-hmm.
So with single terms, maybe try just the comparison test because it's way easier. Okay. With multiple terms, you're going to look at what it looks like, how it behaves. How it behaves is with the leading terms. So we base it on this one, then we take a limit of a sub n over b sub n, and we do the limit comparison test. We okay with that one? Are you guys sure? Am I going too fast for you? Okay. Next up, this is just straight up, automatically, what? Alternating series. Just do alternating series test with that. It's really easy to see that it is decreasing. It's really easy to see that the limit is going to be 0. Alternating series test, and you're done. With this one, you actually have an option. You can do either the root test or the ratio test with this. It doesn't matter. So pick either one of this. The root test is a little tricky because you have to make n be something to the nth power. It's possible. It's just not easy to do. Well, it's not super hard to do. You can do this. N to the first is the same thing as n to the n over n, which is the same thing as n to the 1 over n to the n. It looks weird, but you can do that. And that way you'd have this ratio appropriately. The last one. When you get down to something like this, please do not start doing weird things like a ratio test or a root test when you have a sign all in there already. Is that going to work out for you? It's not alternating. So when you have something with a sine or a cosine or something like this, do the absolute value first. Because as soon as you do the absolute value, so use absolute value, as soon as you do that, then you can say, well, the absolute value of sine is always less than or equal to 1. Does that make sense? And then you have this comparison test idea. So try absolute value, and then you'll be able to use one of these other tests. I'm going to put then, use something else. Use a comparison test. Did this help you at all, this summary? Show of hands if you feel okay with that one. Okay, so this will hopefully give you an idea of what you can do. This is every test that we've done. There's a lot of tests, but now you have at least an outline. Did this section make sense for you? All right.